So please stop me with questions. Since this is a summer school, if it was virtual, you won't have to ask anything. But since this is in person, let's just try to do this as interactive as possible. So yeah, I'll talk about model pruning and lottery tickets. Is this too loud? A bit too loud, I know. I'm sorry. Anyways, so the first part, I will talk about model compression and the lottery ticket hypothesis. Who knows what model compression is, or maybe hear a little bit? Who has no idea what model compression is? Great, you will hopefully know what it is. Lottery ticket hypothesis. Some people know. Okay, so this is the exciting new stuff, I think, in model compression. So the second part is going to delve a little bit into more the theory and some kind of like advances, late advances of model compression from the lottery ticket hypothesis point of view. But let's start with the first part. My aim is to end by 12. So I'm sure you've seen these curves, right? So this is basically accuracy versus number of parameters. And these are kind of like different families of models. So, efficient net, ResNet, amoeba net, whatever. So what do we see here? So we see that the scale increases as, or the accuracy increases as we increase the scale. And kind of like on the larger side of things for model, for vision, kind of like half gigs. So it's not too bad. We can fit on a V100. We can run mini-batch training and whatnot. But nevertheless, these are large models. Okay. The situation is a little bit ridiculous with language models, right? So I don't know, you've probably seen this. This is from, I think, Microsoft's or NVIDIA's blog post. So this is now model size. How many parameters do I have versus years? What do we see here? This is exponentially, this is an exponential or log plot or whatever. So the models have been increasing exponentially fast, okay, with regards to the years. And GPT-3, you probably heard about it, very, fancy language models. They're huge. Megatron is also huge. They're kind of, 1 terabyte. Can we fit this on a single GPU? No, we can't, right? We can't even do inference on these models. So if I were to give you this model and I'm like, here's a V100 GPU that costs like 10K, you can't even do inference on it. So that's a big issue, I think. It's kind of like here to stay. I don't know if you've heard this kind of like scales all you need type of phenomenon. Mike talked about it. People talk about it on Twitter. There's a lot of hot takes about it. But the main point is that by increasing the number of parameters, something weird happens that was not happening in our traditional machine learning thinking. This is good for optimization and learning. So you increase the number of parameters compared to like, the number of data points. You have like 1,000 more parameters than data points. If you were to take a VC dimension type of a bound or like traditional learning theory courses, I would tell you major no-go, this is not gonna work. Guess what? It works in practice, and this is in fact the only thing that works. We need more parameters than data points. It also helps optimization. This is something I kind of like found out recently. Sometimes optimization becomes faster because of more parameters. So you need less number of passes over the data if the model is larger. This is completely insane. Nobody understands why it happens, but it does. And that's why we like scale. So this trend is not going away anytime soon, as far as I understand. And it brings a lot of challenges. The biggest, I think, philosophical challenge is research. I won't talk about this, but the point is that from us here, basically Mike can do this kind of research. He has access to like hardware. But like academia, we can't like even have our hands on like, these huge models. And we can't even do, like even if you have Someta released a really nice GPT-3 type of a model called OPT, you can play with it if you have 100 GPUs or something, right? So it's like really, we're really limited by that scale. So it allows practitioners to like make these models extremely impressive, but they're really hard to deal with. The reason for it is being, a lot of parameters are basically implying a very large compute, storage, memory, any resource type of a footprint, energy, right? Everything goes up with scale. Especially if you talk about edge devices. So when I was thinking about edge devices back, a couple of years ago, I was thinking about mobile phones. But like even your laptop is an edge device. Like you can't, like if you want to do inference even on like, a large ResNet, you can't really do it because it doesn't fit in RAM, right? So think of even your laptops as edge devices, things that just don't have, 100 GPUs and 1 terabyte of RAM. So everything else I would call an edge device, like something that just can't even do inference for these types of models. So the question is, are we completely lost? Maybe a little bit, but at least we can do something about it. And what we can do is what people call model compression, right? So that's what I'm going to talk about today. Any questions so far? All good? Yeah? Yes?
So scale helps us train.
Yeah.
Makes inference painful. What about techniques? Are you going to talk about compression as one, I guess? Is the idea to take a pre-trained model and help it, make it of a size that can be used for inference, or are you also going to talk about training in this way too?
So yeah, so we're going to try to think about how compression can eventually help us even during training. So traditionally, we'll see it has been thought of more as like, fast inference, but with the advent of lottery tickets, we're hoping that maybe it can help during training. Great segue. Awesome. The professors should not be the only ones asking questions. All right, it's a summer school for students and postdocs. All right. All right, how do we compress a model? Who is an electrical engineer here? All right, I got a few. You take information theory, I hope, and you've seen labels if and how you compress data and whatnot. That is not how we compress models, right? So it's very different. So the biggest difference here is the following. So you want to minimize some discrepancy between the source model and the compressed model, all right? We'll see what that means. Typically, you just want the compressed model to have the same loss as the original one. Basically, the performance or the accuracy to not change. Otherwise, why even compress, right? Okay, but you want to do this while making sure that the bits that model takes, like how big it is minimized, or it's small to the extent possible. So the biggest difference with data compression, if you come from an electrical engineer background or you've taken information theory, is that typically you have kind of like an encoder-decoder setup. For model compression in machine learning, you don't have an encoder-decoder. You just have a smaller model overall if you were to count the number of trainable parameters, and you want that thing without any fancy decoding to just work out of the box, right? Good. So how do people compress models? I'll tell you how they used to do it, or I guess, yeah, so these are all the techniques. So as you can imagine, this has, it has interested researchers since the 80s. So the first model compression paper was back in the 80s, I think from Jan LeCun. It was called Optimal Brain Damage. Pretty fancy title. Anyways, so the traditional way of doing it, or the most popular, is sparsification, killing off weights, right? So I have a bunch of parameters, throw away as much as you can without affecting the performance of the model. The second one of my favorite ones, but I'm not going to talk about it, is structure pruning or structure compression or factorization. In this case, what happens is, think of like, having a weight matrix W, you replace it with like two factors that are of smaller dimension, let's say U and V. So you have twice as many weight matrices, but now they're much smaller. So although this is kind of like, let's say, a square matrix, these are like, there's a tall one and a wide matrix, all right? So you do reduce number of parameters. So this is kind of like more modern, I would say, has attracted interest. The past 5 years, typically you will hear it as like structured or factorized type of pruning. I won't talk about this today. Another one is called distillation, where you start with a large model and you try to just have a smaller one, like literally something that's like less width and less deep, but has the same performance. There's an intricate way of making this work. And there's a ton of other stuff that basically relate to how you can compress individual weights by maybe quantizing using low precision, bunching them together and do something that's called weight sharing. We won't talk about this either. And the last thing that's very interesting is people have tried to, from scratch, create architectures that are small and work very well. There's been a ton of work. There's probably thousands of papers across all these dimensions of compressing models. We will focus on the first one. So just killing off weights. This is the more traditional, maybe more natural to think about, where you literally try to kill off as many trainable parameters as possible in an unstructured way, all right? Questions? Mike? No, I'm kidding. Anybody from Mike and above? Everybody good? Okay, great, awesome. So why is like the whole area fascinating? I'll talk about a few baselines. But the main point is that model compression can lead to tiny models 100 times smaller than what you start with zero loss of accuracy, okay? So that's the big selling point. So you can make something 2 orders of magnitude smaller, no effect on accuracy. All right, how do these guys do it? We'll check on the next few slides. It is fair to say that across all these 4 dimensions that I talked about of different ways to compress a model, this is true across almost all of them, okay? Okay, let's see. So I'll see what happened from the 80s until 2018, from the optimal brain damage up until, kind of more recently. what I'm going to say is not necessarily fair, but like the vast majority of model compression algorithms falls under the following category. You start with your architecture, think of ResNet 50, whatever you want to train. You randomly initialize the weights, Gaussian weights, let's say, whatever you want. You run SGD to full accuracy, so until you fit all the labels, okay? But then this model is still dense. So what do? You say, okay, you know what, I'm just going to throw away a few of those weights. How do I do it? There's many different ways. One classic way is just looking at the absolute values and saying, I'll just throw per layer the bottom, let's say 20% of the weights, okay? So you start sparsifying the model. But that has an effect. The effect that this has is on accuracy. You start losing accuracy, all right? So how do I regain accuracy? I can go back to the model and retrain it. Either just the surviving weights, or maybe I can put back some of the other weights in the training game. But the point is that still after you do that retraining, you only have a model that's maybe like 80% sparse rather than like 1% or whatever. So you keep repeating this loop, right? So you sparsify and then you retrain and you sparsify and you retrain, and that is followed by a full, or like this is after a full training with SGD, okay? So again, this is not every single work that has appeared in the past, but it characterizes a big majority, a big chunk of the model pruning type of work. And I want to talk about a very simple, not simple, but a very classic by now baseline called deep compression that maybe you've heard about. That kind of like falls into this category. But before moving forward, I just want to take a 3-5 second pause to see if there's any questions. Yes?
When you go back for the train, if you use some weights that are not the same, doesn't mean that you have to store the full network somewhere?
Yes.
So if we do threads, how do we fit it if it's one of the big models?
Correct, yes. So the goal is that at the end of this expensive loop cycle, you will have something that's sparse, and you can use a sparse data structure to store it. But you're getting into the sort of the main pain of these algorithms, where it's like during the whole process, you do need to maintain a large model, and you do need to essentially train a very dense model, which is one of their major disadvantages. But by the end of the day, you will have something that's very sparse. Yes?
When I start cutting away weights, I end up with sparse matrices. However, the most architectures I run my models on require dense matrices.
Very nice. Yes.
How does pruning influence performance in terms of runtime?
So I'll show you one of the baselines, the deep compression, where they get something like 100x compression or 50x compression, and this is only translated in 5x speedups, which is not proportional to the sparsity. This happens precisely the hardware that they were training on, and the system is not optimized for sparse data structures. So you have to be very mindful of how you do it. You literally have to build a new system that's optimized for sparse data structures, or you can use factorized or structure sort of sparsity, where instead of sparse matrices, you use skinnier matrices. I won't talk about this, but this is something that's also a very exciting direction that tries to kind of ameliorate the issue that you just raised. Yeah, very good question. Was there one more question? All right. Yes?
Do you think that this approach may be good only if the initial model is other side?
Yeah. That's a great...
If I have a model that I can train it, let's say, for 300 epochs or even more, and then I get 50% of accuracy, I think there's no chance that this process can do something.
Absolutely. So this kind of let me take a step back. Is every model compressible? No. So the goal here is to take those models that are very accurate. Remember those curves that with the accuracy versus number of parameters. You push more parameters, you increase the number of parameters, you get more accuracy, right? So people want that, right? So you kind of want to go at the edge of that spectrum where you have a lot of parameters and see what happens there. If you were to go if you were to look, for example, at something like MobileNet, I'm not sure if you heard about it, it's a very compressed type of edge deployment model. These are not compressible, right? So this does not work for everything. So you can say, okay, why don't you start with a small model instead? And the answer is accuracy. You just won't get to that target accuracy. And that's the interesting thing, and the whole interplay between over-parameterization and optimization and learning, that you can take exactly the same number of parameters, put them in a random network, start with that and train it, and it just won't reach the same accuracy. Why does that happen? We have a lot of theories, I should say a lot of conjectures, but not concrete theory that characterizes it. Great, yeah, very good. All right, awesome. Was there anything else? Sorry, my side vision is terrible, yeah.
I was wondering if there's not like a kind of chicken egg problem here.
Yeah.
You need to be able to train full model.
Yeah.
So that you could compress it. So meaning you have the Google.
Yeah.
To do that, right?
Yeah. Exactly right. Exactly right. Yeah. So in this case, you can't really avoid this. So we will go back to this idea of maybe starting as early as possible with a very compressed model, and whether this is feasible. Yeah. Great question. You folks are great. All these are segues for the next slides. Awesome. All right. So let's talk about deep compression. This is a paper by Stanford. In 2016, I believe. And I would argue that it's a combination of methods, but the biggest boost in compression is obtained through this train, prune, and retrain approach. So deep compression has three components. So the first component is sort of a pruning component that precisely does the train, prune, and retrain type of an idea. What do they get out of that? Out of that, they get around 9 to 13x compression of, this is not for all models. Think about, let's say, VGG16 or whatever. There's a second step that now they say, look, why use floats for the weights? Now you can compress the individual weights. How do you do this? Well, per layer, I will run a k-means clustering on the level of the weights. I will have instead of having if my layer has 1,000 weights, I'll instead say, use 10 centers, right? So 10 quantization levels, and I will create those quantization levels through k-means. Once you do this, well, you can retrain those centers and readjust the sort of the k-means optimization. So if you do this, you are able to save significantly on, basically the precision, right? So I don't have to use 32-bit floats. I can just use, let's say, k numbers, where k is the number of the centers. How much extra compression do I get? I go from 10x to, let's say, 30x. So an extra 3x just by compressing the precision, let's say, of the weights. And the last step is something that is, again, familiar to those of us that are from electrical engineering departments. You use Huffman encoding. So you take those k-centers, you do Huffman encoding. The reason why it works here, you don't really, the decoding is really fast. If you know how Huffman works, you kind of read the stream of bits and you parse the tree of the compression, and you kind of spit out the compressed weight. Anyway, details that are important, but not for this talk. The main point I want you to take out of this is that at the end of the day, this sort of train, prune, and retrain method achieves 50x compression, all right? Back in the day, so this was in 2016. This is also true. It's a very strong baseline even now. On most modern data sets and large models, it is able to achieve a significant amount of compression. Okay, yes?
So with this Huffman encoding, when you want to use your model, you have to first decode it. So
Yeah.
it's just for the hard disk.
So you could use this during inference. Of course, you have to use optimized data structures and whatnot. But the good thing about the Huffman encoding is that it's a symbol by symbol encoding. What that means is that you read a stream of bits and that maps to a symbol, right? Versus, for example, Lembelziv or whatever, some other block type of compression, you would have to do exactly what you say. It's good for storage, but for inference, you have to decompress the model. In this case, you don't really have, you just read the stream of bits and you map it to whatever it is. Right? Yeah. So maybe the main thing I want you to take out of this whole thing is that the biggest boost in compression is the first, train, prune, and retrain type of a method. But okay. All right. So what do they get? So I won't go into details, but that was back in the day. People were running stuff on MNIST and of course ImageNet. So on ImageNet they had AlexNet and VGG. They were able to get pretty significant compression rates. What is also significant is to look at the top one error that they got for the compressed model. So for every block in that row, the second, so the first one, the reference is the uncompressed model, and this is the deep compressed model. Check the accuracies that they get. Right, so the comparison between the accuracies of the compressed and uncompressed is pretty stunning, right? So you don't lose anything by doing that. So that means that there's a lot of stuff you don't need in the neural network that you should throw away, okay? And of course, people knew about it before, but this paper was striking in its sort of level of compression that they managed to achieve, all right? So this is like, 2 orders of magnitude. You go from, I don't know, like half a gig to like 10 megabytes. So it's pretty significant, I would say. And these are usable models. You can do inference on them. So in terms of like, the benefit with regards to like efficiency, power efficiency, and consumption and speed, you don't really see a 50x improvement. And this goes back to this great question that your colleague asked, that things are not really optimized for sparse data structures. So different discussion, very interesting problem on the intersection of machine learning and systems. But this is mainly the main reason why sparse models out of the box are not like as fast as their compression rate, or as more efficient as their compression rate. Nevertheless, I would argue that this is a very strong indication and evidence that network pruning works in the sense that you get something that's very small and has the same accuracy as the huge model that you started with. All right. Any questions? Yeah.
So this is the top one there, I'm guessing on the ImageNet validation set.
That's right, yeah.
Is there a sense of what these kinds of methods do to robustness of distribution?
Yeah, that's a great question. Yeah. So the main thing with network pruning is that you look at a single, you basically project the entire model into one number. You're like, I want to preserve, let's say, accuracy. But there's been a lot of great work by a lot of folks trying to figure out the effect on, let's say, look at fairness type of metrics. So like, when you do pruning, does it like, have a negative effect on like accuracy of subpopulations or whatever, or, robustness? And the answer is it does. In fact, if you were to look at kind of like losses at subpopulations, pruning is actually pretty bad. Like you have to be a little careful about how you do it. Robustness, I don't know, like in terms of like adversarial robustness, I would say they're all bad, right? So the prune and the unprune model. So the out of distribution, I'm not sure. I've seen papers that talk about it, but I'm not sure what the kind of like the, what the outcome was. I do know that there's an effect. So it's not, this is not for free if you are interested about other metrics. Great.
Yeah, actually, I think there exists a paper to argue that similar effect of the lottery ticket apply to the robustness.
Mm-hmm.
And they argue that there exists a subnetwork that is robust to the different distribution.
Okay.
Yeah.
Awesome. Yeah.
So you've got figures for compression in terms of bits, number of bits, which I think you were asking about. That's great for maybe data transference
Mm-hmm.
or network or storage or something, but in terms of, you still have to recreate the whole network.
So here you don't, yeah.
So do you have any feeling for how small are those networks to compress networks in terms of numbers of parameters?
Oh, okay. So let me just try to understand the question. So you're asking if you just was looking at compressing the weights, not interested about inference, how smaller it would be compared to like the pruned ones? Is that?
Well, it's a multi-step process, right?
Correct.
You do pruning, and then you do this quantization stuff, and then you do this Hoffman coding.
Right.
So the last two of those steps is about reducing the number of bits required to store the model.
Correct.
But the first step is pruning.
Yeah.
Is about removing
Correct.
parameters, right? So if you got times 49 improvement in terms of bits, but what's the reduction in terms of parameters?
Oh yeah. Okay. Good question. So what they managed with the first step here is they were able to get basically like a 10x reduction. I don't know why I can do this, but yeah. So this is what it is. It's like 9 to 13x. So they do get like a 10x, like you get something that's like let's say 10% sparse, but then you can still push with more like the weight compression techniques. And the key with those weight compression techniques is that they don't require a decompression thing. So that's the main, or at least it's not expensive. Yeah. Yep. Great. All right. So, okay, so what's the current state of the art in model pruning? I would say it's a messy world. If you want to learn about it, I would go and read this phenomenal paper that was released at JMLR last year by your colleagues at ETH Zurich and IST Austria. So they compare a lot of methods and they give clarifications about a lot of things, but the main point I want you to do, kind of like take out of that is that there is a very interesting high-level picture that I'm borrowing from their paper, that basically tries to understand how much sparsity or how much compression can I push on a model before it breaks down. So what breaks down means is that, the accuracy, no matter what you do, whether you're a magician or not, at some point you just can't throw away more stuff. So how does the trade-off look between, sparsity and accuracy? And what they say is the following. So here I have sparsity, like how small the model is. So in this case, just like, with regards to like active weights. There's two curves. So the green curve here is accuracy. So something interesting happens to accuracy. As you sparsify, test accuracy increases, but then there's a phase transition that kind of like it dies down. That transition is where you're like, there's no, you can't throw away more stuff without a penalty in your accuracy. On the other hand side, there's a red curve that is performance. What does performance mean? Faster inference, smaller memory footprint, smaller storage. And this tends to kind of like, be, let's say, linearly associated with a sparsity factor, and then kind of like plateaus. Why? Because, again, you reach a system wall where it's like, if you make something sparser, it sometimes can become slower too, It's like, it's unclear whether you will actually get the benefit. For me, the most interesting curve is the green one. So there is this thing we have not really understood, like this sort of phase transition of performance, where you kind of like, you're a little better at some point, like your test accuracy is better when you sparsify. This has explanations from like generalization theory, where like a simpler model maybe is better. But then you have this like very rapid phase transition that we still don't really understand very well. Anyways, so there's another great paper that talks about state-of-the-art type of pruning, and tries to compare a lot of methods. So this was released at MLC's 2021, and it compares a ton of stuff: structure and unstructured pruning, lottery ticket algorithms. I will talk a little bit in a bit, more classical deep compression type of algorithms. So what's the state? You kind of have to read the paper. So it is pretty. I can't tell you what's the best algorithm. It really depends on the data set. I would argue that they kind of like all work pretty well. You can squeeze a factor of 2x better performance in comparison to like the worst and the best, but it's a pretty busy space. Convincing comparisons at this point is a little bit, they're tricky, and the benchmarks are tricky because everybody kind of like, they say, okay, here's what happens for CIFAR10 and my neural network, and another group says, here's what happens on like tiny ImageNet and a different neural network, and it's there's no sort of like a uniform, let's say, baseline. This paper suggests a set of guidelines on how you would compare your pruning methods. But if you want to keep something out of the slide, is that it's a busy space. It's a very busy space. So if I were to kind of like summarize maybe the philosophy or the meta algorithm of those pruning approaches, I would categorize them under 4 sort of meta approaches. And again, this is only for weight sparsification. So forget about the quantization factors and all that. This is just like throwing away trainable parameters. The traditional one is this idea of train, prune, and retrain. So in the 4 figures I'm going to show, the sketches is just sparsity, like how small my model becomes, versus number of epochs or passes over the data. So the first one is the train, prune, retrain type of method, like deep compression, right? Where for the vast amount of time I spend it just training a dense model, and then I sparsify a little bit, and then I sparsify a little bit more, and then I sparsify a little bit more. Again, the levels are how many parameters do I have remaining in my training, and the x-axis is just my epochs or passes over the data or iterations or whatever you like. Another approach that's very popular is the prune while training approach, where you do kind of like a successive or a soft thresholding at every iteration. You deal with a dense model for a little bit, and then for a little bit more you deal with like a sparser model and so on and so forth, and kind of keep decreasing the sparsity. So this is the pre-2019 era, okay? In 2019, something interesting happened that I will talk about in the remaining of this talk, which is the lottery ticket hypothesis, that basically said that somebody here mentioned this. Why do you have to deal with a dense model from the beginning, right? Why don't I just throw parameters at initialization and see what happens? So this is the idea of pruning right at initialization without even doing anything to the weights. Without training the weights, can I do anything intelligent in the beginning so you can sparsify things away, and then you can just train a sparse model from the get-go. And there's something else called prune a little after initialization. Do a little dense training first, see what happens, and then start sparsifying at that point. These two techniques are very related, and I will explain how in a little bit. But from a high-level perspective, I would say that the sort of the train, prune, and retrain, where you deal with a dense model and you just care about compression, it has cooled down a little bit. And what people care a lot about is this sort of post-2019 pruning that happens after or at initialization or soon after initialization. The reason for that, the reason for the excitement about this type of pruning is because not only it will give you a model that's compressed, but it will also give you a model that is easier to train. Why? Because you're going to be dealing with a small number of parameters from the get-go. All right. So that's the main appeal of this pruning near initialization type of technique. Okay. Any questions on this sort of? Yes.
What are the criteria for the pruning in this hypothesis? For example, you mentioned the structured and unstructured criteria. What are the criteria in this?
You mean to classify them under those sort of 4 families?
Yes.
Okay, so, okay, good. So basically, the way to think about it is, let me just see if I can get rid of that. But anyway, so the way to think about it is the following, that the sort of the blue part, the pre-2019, is dealing with, while compressing the model, you deal with a big model for most of the, the algorithm. So that's the way to think about it. For the post-2019 methods, the pruning close to initialization is kind of like trying to get rid of the dense model as fast as possible, so you don't have to compute a lot and you don't have to store a lot during the whole process of training. So think of like, the amount that I need to train overall is a fixed budget, 1,000 epochs. How many of those 1,000 epochs, let's say, do I deal with a dense model? So that's kind of like the way to think about the two different families of pruning algorithms.
Are they done randomly or by a method or something like that?
So you mean these methods?
Yeah.
So I'll talk about it in a little bit. The whole point is to show that when you do this intentionally, let's say with a proper algorithm, it should perform much better than randomly selecting weights. And we'll go back to exactly this point in a few slides. Very good. Yeah. Okay. Any other questions? Yes.
So this pruning at initialization is basically just finding a good architecture with initialization to train, right?
It is very related to something called network architecture search. It is sort of trying to find a good architecture, but this is not enough. As we'll see, what kind of like the winning recipe for this pruning at initialization algorithms is to find a good combination of a sub-architecture, but also the weights assigned to the surviving edges. So you can't throw away, so you randomly initialize everything with Gaussian numbers, you find a sub-architecture, and the combination of sub-architecture and original random weights is kind of like the winning recipe. If you were to throw those away, you would reduce the performance of the downstream training algorithm. We will see this in more detail in a few slides. A very good point. Okay. So, all right, let's see. So I'll talk about the lottery ticket hypothesis. Now that relates to all the questions that you folks just asked. So in I guess, I don't want to repeat myself. The main issue with this more traditional network pruning type of algorithms is that they were geared towards faster inference, but they just didn't care about like faster training. However, in the presence of ridiculously large models, you would also like faster training. And you would like to get rid of like really expensive type of like dense training loops in the beginning of your compression algorithm. So in 2019, Jonathan Frankel and Mike Carbin from MIT, who actually got the Best Paper Award for this idea, for this paper, suggested the following. So they had the hypothesis that now is called the lottery ticket hypothesis, that basically suggested that maybe at the beginning of training, maybe even before you do anything to the network, there exist sub-networks at initialization that if you were to magically find them, we'll talk about the magic of finding them in a little bit, but if you were to magically find them, you wouldn't have to worry about pruning anymore. Just find something that's very sparse, be lucky about it, win the lottery. And if you were to get access to that, you just have to train this once to full accuracy, and that's it. Okay. So the main key here is to, how do you win the lottery? But again, the main premise of this idea is that maybe you can completely avoid the burden of training a dense model before you sparsify and compress it. Okay. So of course, this idea had a lot of, there was a lot of excitement. They won the Best Paper Award. There's I don't know, thousands of papers that came after this. And if you were to ask me, up until 2018, should I work in model compression? I would say, forget about it. There's been a ton of work. In fact, a student of mine came and said, I want to work on that. I'm like, there's just, too many things that have happened already. I don't know if we can make any meaningful contribution. But then this paper came out, and then we kind of almost my entire group sort of jumped back in model compression. Jokes on me. Anyways. So what are lottery tickets, all right? So lottery tickets have to be special, all right? In what way? In the following way. If you were instead doing just random sampling, your lottery ticket should be better than a randomly sampled subnetwork. What do I mean by that? So let's say I randomly initialize my architecture with Gaussian weights, and I take a random subset of those weights. How do I do this? Let's say I will pick the same sparsity level per layer as the lottery ticket. All right. So you gave me a lottery ticket, and I just look at the sparsity levels per layer, and I just use that with a random sampling algorithm to get a random sparse subnetwork at initialization. If what you claim is special, it has to train to better accuracy than training a random sparse subnetwork, right? So lottery tickets should be trainable to better accuracy than sparse subnetworks at initialization that have been just randomly selected, okay? Otherwise, you're not finding anything interesting, all right? Does that make sense? What kind of makes, let's say, lottery ticket special? So you have to do something intelligent at initialization. Otherwise, what's the point? Just randomly sample, okay? So just a little bit more, not necessarily formal definition, but a lottery ticket is a subnetwork that's at initialization before doing any training, trainable to better accuracy than a fully trained, randomly sampled subnetwork of the same sparsity. Okay. So how did they find them? So in the original paper, they suggested an algorithm that is now known as IMP, iterative magnitude pruning, that is actually very reminiscent to the train, prune, and retrain type of algorithm, with one difference, that once you prune, whatever weights survive the pruning phase are going to be rolled back to their initial value, all right? So you train for a bunch of epochs, in fact, a lot of epochs. You sparsify according to just keeping the highest magnitude elements. And whatever survives, so whatever you throw away is never going to be part of the game anymore, but whatever survives is going to be rolled back to the initial values. Once you do this and you get a model at some point that's, let's say, 1% sparse, you take that and you train it to full accuracy, and you see how that performs in comparison to a randomly sampled subnetwork. There's a bunch of things to note about this algorithm. The main thing is that it's super expensive. They actually run it for a lot of epochs. This is more expensive than deep compression, all right? But the paper is trying to make a point. The point that they're trying to make is not I can do this fast, but look, there's these special subnetworks that exist at initialization, and that's what you should be looking for. And maybe you can do it much faster than IMP, all right? So their algorithm is very slow. It's not really, you wouldn't use it for faster training because, you do have this train and retrain thing that happens at the pruning phase. But what they give you is a sparse subnetwork at initialization with weights that are random. Random in the sense that are frozen to whatever initial value they had, okay? Just going to take a little pause here, have a few more minutes. I want to make sure that this is parsable to all of you, because if you don't get this, then the rest of it is, you'll get very sleepy. So this is kind of, yeah. Any questions? Yes?
How transferable are these if one of these subnetworks is good for one data set?
Yeah.
Also good for another one?
Great question. There are claims that they transfer, but it really depends on the data set. The hope is that they should transfer, but yeah, it really depends on what model you start with. And it really depends on what kind of like downstream task, like if you were to do, let's say, fine-tuning, what downstream task you're looking at. So there is a BERT paper for lottery tickets that kind of deals with this a little bit. And there's also a lot of work on fine-tuning and seeing how, the sparsity levels are transferable. But I would argue that we are at a stage in the lottery ticket hypothesis where we haven't even cleared up the question of whether these are actual special lottery tickets. So or I should say these are actual special subnetworks. So I'll come back to this. I'm just running ahead a little bit. But yeah, it's a good question. Yes.
Is there like some correlation between weights, the initialization, and the weights which stay in the network?
It is, I would say it's unclear, yeah. From the experiments that they had, at least in the original paper, it was not clear if there is any sort of relationship between, let's say, the magnitude of the weights and whether they survive or not, yeah. That's a good question. This is a very, you can test this, right? So, we could run the experiment and see how it looks, but I don't know. This is a good experiment to run.
Yeah, but like, for example, if you train it like several times,
yeah.
The same weights stay, or like you just independently do several times this procedure.
Oh, I see. Typically, you get very different subsets of weights. Yeah.
So like even if you initialize, start from the same initialization.
Oh, yeah. If you start from the same initialization, yeah. So the problem is the following, because if you run SGD with exactly the same randomness, it will, or this algorithm with exactly the same randomness, it will give you exactly the same thing. But if you, let's say, do there is a mini-bud sampling that happens here because you do training. If you have this random across two different runs, you will get different subnetworks. Like the whatever weights survive will be different across these two different runs, typically.
Even if like initialization is the same?
Yeah, even if the initialization is the same. So that doesn't, that by itself doesn't necessarily mean that these two different things are not, maybe what you find is not meaningful, right? That's probably a conclusion of that experiment. But I would say a more optimistic conclusion is that there is such an abundance, let's say, of trainable networks, and that's why we see, that's why you can just pick different ones when you have different runs of this algorithm. Very good.
So what pruning strategies use another many effect on finding these lottery tickets?
What pruning? So the way that they do this here is that just absolute magnitude, just like kill the smallest magnitude elements for every iteration. So here, you train for a few epochs. You prune, let's say, 20% of the smallest weights, and then you roll back whatever survived to the initialization. And you repeat this again and again for many times. Yeah.
You mentioned that the pruning in this method is done based on the magnitude of the weights.
Yeah.
It means that, for example, if the magnitude is below the threshold,
right.
This one would be prone.
Yeah.
And is necessary the value of the magnitude correlated with the importance of that weight or not?
That's a very good question. So, yeah, sorry, continue. No, this is a good question. So why is magnitude important? Yeah. I don't have a good answer, apart from the fact that everything else is expensive to compute. There was a very interesting paper by Uber that, I don't remember the title now, but basically they tried to figure out what is a good pruning metric. So they look at amplitudes, or, for example, to me the most interesting metric that paper was looking at during pruning is look at the progression of the weight when you train it and see how much it changes. If it changes a lot, maybe you should keep it. If it doesn't change at all, maybe you should throw it away. So they tried a bunch of these different metrics, and they found out that magnitude pruning is kind of like as good as anything else. Yeah, it's. I don't have. There are other methods based on entropy. There's a nice paper called SERP, again by some folks at Stanford, that looks at like entropy measures for pruning. But these algorithms are really hard to beat. The magnitude pruning ones, I mean, yes, maybe you can get something better, but it's not going to be like 1,000 times better. Yeah, and it's very cheap. That's the appeal, right? Yeah.
So rolling back is clearly important
Yeah.
to make this recipe work. Is there any understanding of what is the property of the network once you roll back?
Yeah.
Is there something that's preserved, or is there something that any intuition for why this works so well?
I would personally argue that, I mean, when I saw the algorithm for the first time, I would be like, why would you ever roll back? It just does not make any sense, right? But there is something that happens at initialization, and that's going to be part, hopefully I will have time to talk about it during the second part of the talk, but there is some sort of learning that happens at initialization, but it was not clear from this algorithm. In fact, so I think we're over time, so I'll just try to wrap up in the next slide. Is that right? Are we out of time? We're like a few minutes out of time. Yeah. Okay, good. So, yeah, this is a great segue. These are all great points. So, let me see what I want to recap. If I want to recap, or I want to. This is literally the half part of my first, the half middle slide of my first presentation, but it's totally okay. And let me just maybe conclude here so you folks can have lunch. Just don't eat too much and so you won't get too sleepy for the second part because it's going to be a lot of stuff. But so they did a lot of the tests that I think you suggested. So like, what if we initialize the weights? Or what if you do kind of like sanity checks on the lottery tickets? And they found that lottery tickets are special experimentally. And this is precisely what ignited a lot of interest in the area. What did other people do? Faster algorithms, single shot pruning, subsets, using subsets of the data, BERT, language models, blah, 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 a bunch of stuff. And something very interesting happened short after. They figured out that these algorithms don't work unless you do stuff on MNIST and whatnot, right? What do I mean by that? I'll close with this slide and we'll come back on this one. A lot of folks, including Jonathan Frankel himself, he ran experiments on ImageNet. And he saw that IMP, when you run it at initialization, was finding neural networks or random subnetworks that basically would perform equally well when fully trained in comparison to randomly sampling a network at initialization. That's very sad, I would say, right? So kind of like the first paper kind of like seems to like not hold beyond just MNIST. And there were a lot of other papers that kind of like figured out the same thing, right? So there were a lot of papers that basically said not just Frankel's algorithm, Jonathan and Mike's algorithm on magnitude pruning, but all the other algorithms that basically were claiming to find lottery tickets were finding essentially just good sparsity levels, right? So that was literally the only thing that was happening. And there's, when we come back, I'll talk to you about the sanity checks that people run and what kind of like, the experimental concrete evidence that all these past works were finding just good sparsity levels. Why is that valid? And we'll see kind of like how that plays with what can we do at initialization anyways. So enjoy your lunch and I'll see you all in an hour. Yeah, so just to recap a little bit what the original lottery ticket hypothesis paper sort of suggested, they said that, look, there are these very special networks at initialization that if you were to find them, you can train them to full accuracy without having to worry about pruning again. And kind of the main point was that, these networks were, in fact, better for those tasks than just using, a random subnetwork. In fact, they did run a few experiments on like MNIST mostly, where they trained, random subnetworks and lottery tickets, and they did find there was a significant gap between the accuracy. So this is basically test accuracy versus sort of sparsity of the respective neural network that you train. And there was a big gap at that point for that particular architecture. And those particular data sets. This is what kind of like really excited the scientific community and kind of like everybody sort of started thinking about lottery tickets. So, as I kind of like concluded last time, there were a lot of papers that basically used a bunch of sanity checks to essentially show that what these guys were finding were not really anything more special than carefully crafting the sparsity levels of the random networks that you would train. So although for MNIST and for Lenet and whatnot, Frankel and Carbin were finding, lottery ticket special subnetworks, on CIFAR10 and ImageNet, this was not really transferring. So what were the sort of sanity checks that people tried? Let's see. I don't know why this keeps writing with my finger. Sorry, folks. Let me fix this. All right, maybe this is better. It's not. Anyway, whatever. So, yeah. So here's a few sanity checks. So if you were to give me something that is called a lottery ticket, I need to make sure that it's special. How can I make sure that it's special? Well, give me that sub-architecture, and I will re-randomize the weights. All right. So this is what I would call reinitialize the weights of a neural network. Another thing that you can do is like take all the sparsity levels per layer, like the subnetwork that you have, and kind of like randomly permute everything. All right. So you go to the first layer, you have a sparsity pattern, kind of like shuffle it. Do the same thing for every layer, see what happens. Okay. And the last thing, which is sort of like the most wild, I would say, is like when you do IMP, do it in such a way that you invert the scores. Like you literally sparsify, or like you keep the kind of like lowest amplitude elements rather than the biggest ones, right? So here's what they found. So these are a bunch of different algorithms, SNP, GRASP, SynFlow, from very serious people. And they found out the following, that when you were training the unmodified, so what does unmodified mean? These people were claiming to find lottery tickets. Take that lottery ticket and train it to full accuracy, see what you get, do the sanity checks, shuffle things, re-randomize and whatnot, compare the performance. What should you expect to see? A gap, right? A performance gap. If the performance of the fully trained lottery ticket is the same as the thing where you kind of like, messed up with the structure, you're not really finding anything special, right? Does it make sense? So this is what happened, right? So basically they saw that the performance of, there it goes again. So they found that the performance of the claimed lottery tickets was in no way better than just like, re-randomizing the architecture or the elements. And that's why you kind of like see all these curves aligning together. So what is this again? So this is test accuracy versus sparsity. And this particular one was for ResNet 20 on CIFAR10. So these are the sanity checks that you have to, like if you now claim that you find a lottery ticket, check this first, okay? You have like your lottery ticket should stand strong against just like re-randomizing the weights, right? This kind of, let's say, failure to, be better than random was also an issue for IMP. So if you were to run IMP and do this reshuffling and re-randomizing, you would still see all those curves overlapping one another, all right? So again, what were these folks finding? Really good sparsity level. So if you were to do like hyperparameter tuning on every single sparsity level per layer, you would get something that is kind of like as good as these algorithms. But there would be no more gain in the performance of training those lottery tickets versus random subnetworks. Any questions? Okay. So can we fix IMP, or is it a sort of done deal? And they had some good ideas. So this is another paper again by Frankel and Ari, who I guess is in Meta, right? So he said, look, instead of pruning at initialization, why don't you do a little bit of training first? So do a little bit of warm-up, maybe, I don't know, a few epochs, like a small chunk of your training time, and then do IMP. And they found that that actually helps a lot. So in this figure, what they essentially showed is, again, test accuracy or validation accuracy versus sparsity. And the different curves correspond to different rewinding stages or points. So the blue curve is the original IMP where they would rewind back to 0 iteration at initialization. And as you go down, you rewind at later and later phases. And then they observe that this helps a lot. For example, if you were to rewind to iteration 500, so 500 basically mini batches. If IMP again sort of like does pruning and rewinds back to something, traditionally was the initial point. Now it rewinds back to a later stage, okay? So they found out that this helps a lot. Rewinding fixes this issue of IMP. But it's not at initialization anymore. So these are not lottery tickets anymore. They're trainable sparse subnetworks, but they're not lottery tickets because the definition of a lottery ticket is something that is at initialization, and we're still interested in that because we don't want to deal with a dense model as much as possible. Okay? Any questions on this? So this is IMP with rewinding. This is kind of how this algorithm is typically referred to. And it does pass the sanity checks, so that's kind of the important thing. They basically repeated all the sanity checks that they had for like these algorithms, SNP, GRASP, SynFlow, and whatnot. And this is for IMP with warm-up. And they found that there is a gap. When they compare the original IMP with warm-up, meaning whatever you find with warm-up with the sanity checks, it was better than the sanity checks, all right? This started to put a few thoughts in people's minds that, maybe lottery tickets don't really exist, right? Maybe you can't really do anything smart at initialization. And that's the thing that I would like to go into more detail in the next few slides. But I guess, again, I want to see if this makes sense to you. So again, what I said is like everything claimed to be a lottery ticket was not really a lottery ticket in the sense that it was not more special on finding a sparsity level rather than pattern. But if you were to do a little bit of training, potentially breaking some symmetries at initialization, then you could find trainable subnetworks that are very sparse and much better than random. Okay? Yeah?
So maybe I just didn't fully understand because originally you said that if you take a random sparse network with the same sparsity, it would perform worse.
Right, so this was for their original, so for MNIST that is the case. But when they tried the same thing, so this is exactly the same test, but for ResNet 20 and C410, that was not working. Yeah, yeah. Good. All right. So let's see. So then between the two meta approaches of like pruning at initialization and pruning a little after initialization, pruning at initialization so far does not work, and doing a little warm-up is kind of like what does the trick. However, I would argue that like you still have to deal with a dense model when you do kind of like this pruning a little after initialization, and you would still try to avoid it. So I'm still interested to understand whether lottery tickets are a thing, or maybe we should just stop hoping to find them. Okay. So. So this was the first part. What we basically covered is that compression is possible at very high levels and no accuracy loss. And because model pruning is not, so people have tried to look into the idea of like using sparse updates, and this is exactly the premise of the lottery ticket hypothesis. But of course, there's many open questions because you can't really find lottery tickets, it seems. And the other questions that are not necessarily related to the lottery ticket hypothesis, but more general pruning, is the interplay between optimization, over-parameterization, and sparsity, and this phase transition that happens between sparsity and accuracy. These are things that we have not really understood well at all. So a lot of things to think about. But if you go back to the lottery ticket hypothesis, kind of like to dig a little bit deeper to see what happens, there was an interesting paper in 2020, I think 2019. I think this is one of my favorite experimental papers of the past few years. Go give it a read if you have time. The title is "What is hidden in a randomly weighted neural network?" So this is the experiment that these guys did. So they said, let's try to approximate the performance of a ResNet 34, a fully trained ResNet 34 on ImageNet, by only pruning a random wider ResNet 50. Okay. So what they found, it is in fact possible to approximate the performance of a target network, and this was true for many target networks and for many data sets, by only pruning a random larger network. How larger? So of course, if it was like ridiculously larger, this would not be surprising, but it's only like, a factor of 2 or 3 larger, right? So with a larger network, but not significantly larger, you can just train that, you can just prune that and approximate the performance of a fully trained network, all right? Does it make sense what this finding is? I'll explain it a little bit in more detail, but the main point is this is a pruning only algorithm. There's no weight tuning. You don't touch the weights at all apart from killing them, okay? It's the only thing that happens. And that is sort of expressive enough to allow you to get really high accuracy, all right? This is what these guys found. And I want to explain this a little bit more detail. Oh, by the way, here sparsity is not a goal. So this is just to show that pruned networks can approximate different types of functions or whatever. But the sparsity may not necessarily be like really good, maybe like 50% or whatever. But here's again what this guy said. So you can think of this as like the pruning is all you need type of a regime. And they say that state-of-the-art networks actually live within random networks. Okay, and I'll try to convince you why this is surprising. So you start with an over-parameterized network. You literally only randomly initialize it. Gaussians, even ±1 works. So ±1 random weights. The only thing you're allowed to do is prune them. Nothing else. You don't fine-tune, you don't change the weights. You either set them to 0 or whatever they had at initial value. And what these guys find, well, this is where I'm talking too loud. What these guys find is that you could approximate the performance of a fully trained ResNet. So these are like, this curve here is, fully trained ResNet. And the brown curve and the blue curve are pruned networks. So by only pruning, you can manage to get the performance of full training. This is mind-blowing, all right? So this still blows my mind. This is literally the first algorithm that's not weight training that gets you high accuracy, all right? So how do they do it? Well, basically they use something like, there's still backpropagation and SGD involved, but now on the supermask, kind of like on the sparsification mask. So the main question that would be interesting to ask is whether, like, how expressive is that? Like, can you approximate everything by just pruning, or it's maybe limited in those settings? But before I move forward, I just want to make sure that what I said is parsable and makes sense, because again, this is like an extremely surprising finding, I think. Again, there's no weight tuning at all. You just set things on and off. That's it. Yeah.
I think it's not clear to me one thing. So you have your model, which is ResNet. I mean, the smallest one. There is trained, and I think a certain accuracy on the dataset.
Yes.
Now you take a larger model.
Yes.
And you want to prune it.
Yeah.
To approximate the behavior of the other one.
Yeah.
Now you say that the larger model is random.
That's right.
What do you mean with random? So the weights are random.
Right.
Okay. Then you just prune. You don't train anything.
You don't train anything.
You prune, and in the end, after pruning, the accuracy of this model is like the trained model.
Yes. I'm happy you're surprised. I'm very happy you're surprised, because it's very surprising. It's mind-blowing.
So, and you just prune them by
Yes.
state-of-the-art pruning like...
Yeah, they have a different pruning algorithm. It's kind of like, trying to figure out what edges should I switch off so I can minimize the loss. But it's possible to go to state-of-the-art. Like, if you can see here, I don't know why this damn thing doesn't let me zoom, but anyway, if you see here, eventually.
Now I got the point.
Yeah. Makes sense?
Not really.
Great. I'm glad. Sorry, I have to restart this keynote because it's just like driving me crazy. I don't know why this is doing it. Who is not surprised? Who are the cynics in the audience?
So is it correct to say that you don't do any pruning? Any training? You do train. It's just the training is to choose which ones you turn on and off.
Very nice. Yeah. So there is no weight tuning, but there is learning that happens. And there's training that happens, but I would say a non-traditional one, if you wish.
Yeah.
Yeah.
You're like weighting them by 1 or 0.
Or sorry?
It's like you're multiplying the weights by 1 or 0.
Yes.
That's the training.
Yes. So it's kind of like almost like a binary training type of a thing. Yes. Exactly right. Any other questions on this? Yes.
So this is based on the paper what's hidden in the random within your network.
Correct, yes. So let me ask you this now. Is there signal at initialization? Can we find stuff? Is there signal at initialization? Are there meaningful things we can find at initialization? I would argue there are, since we can approximate these extremely complex functions. And from a first step, I would like to understand what can we do by pruning. All right. So forget about the sparsity. I'm only letting weights be being turned on and off. I want to see how much can I express by that. And there's a trivial answer. The answer is everything if you let me use an exponentially large neural network. Just by sheer chance, I can find everything in there. Okay. So this is not an intelligent comment. This is like, after you think about it, it's kind of obvious. If you don't constrain the overparameterization of a model, you can find everything in that model, all right? The surprising thing is that these guys used a network that's not ridiculously large, only 2 times larger than the target one, the one that they were trying to approximate its performance, and it still worked. So why is that? I don't know how much you hate theory, but we're going to do theory for 2 slides, okay? Very few equations, hopefully. So the first thing we would like, and this is a work that some people from my group have been thinking about for a little time now, but there was this really nice paper by Malak et al. That basically said, yes, you can actually find anything in random networks as long as you're willing to overparameterize a lot. So what do I mean by that? So they said, look, start with a target network that has depth L, all right, so L layers, and the width, the dimension is D, the internal dimension for every layer for now. And here's what these guys promised. They said that if you start now with a network that is twice as deep and much wider, a polynomial factor wider, I can find weights in the random network that can approximate the target. All right. How do they do that? I would argue that it's kind of like, I guess before saying that, I don't know why this is happening. Before saying that, if that is true, you can find anything you want in a random network, all right? So you can find lottery tickets, you can find later version lottery tickets. Let's see, maybe this helps. You can find, optimal lottery tickets with perfect performance that don't need training. You can find whatever you want, all right? But there is something that I don't like about this theorem. And what I don't like is this high requirement on overparameterization, because this is kind of like, if you start with a ResNet 34, this requires a ResNet quadrillion, basically, to give you the same performance, to prune to give you the same performance. The reason for this limitation is that in their proof technique, the main idea is to argue that given access to enough random weights, by sheer chance, you will see the weights of the target network, all right? So remember before we said, well, if you had an exponentially large network, you can find whatever you want. The answer is that if you have a polynomially wider network of this size, you can still find whatever you want, right? It still uses like a simple counting argument type of a proof. But the reason why this is not very satisfactory is, again, because this does not reflect practice. In practice, they only use the model that's only twice as big, okay, to do pruning. Let me take a little pause here to see if this makes sense. Any questions?
But they did that on known networks, right? So if you don't know what the target is, actually you know where to set the threshold.
Yes, correct. So this is an existential result, right? So it says that basically in those bigger random networks, anything that has the size of this smaller network kind of like exists in there, right? And how do they prove it? They kind of like assume knowledge of the target network. But the goal is not so much to provide an algorithm for how to do pruning. The goal is just say, what functions can we describe, let's say, by pruning? And the answer is like anything that is basically representable by this size neural network, which is a polynomial factor smaller than what you prune. Okay? Good. So, all right. Who wants to see a little theorem? Okay, good. Who does not want to see a little theorem? You can take a little Twitter break with whoever hates theorems. All right, so just one very, very quick one. So let's say that you want to approximate the target weight, W, all right? So I would argue this is a neural network, the simplest possible. You put X, WX comes out, okay? Now, here's the idea that these guys used. They said, look, if I had this over-parameterized diamond structure, where basically these xi weights are random uniform random variables, and on this layer, this is just a combining layer where everything is like set to 1 for now, and the activations, it's going to be trivial. I'm going to set them to linear for now. Doesn't matter. So here's what they said. Look, if you do this, yes, by sheer chance, we know that you can find your target W. Why? There's a very simple union bound that you can take to say if I choose from those x's the one that's closest to W, it will come epsilon close W as long as the number of x's that I sampled is 1 over epsilon, all right? Sample 1 over epsilon weights, you will get epsilon close to whatever target you want, of course within some bounded domain. So it's a very simple type of an argument. This is in fact how you can create random epsilon nets to cover the space. Anyways, details that don't really matter. What matters here is that if you follow this technique, you will be bound by this polynomial over parametrization. So if you do this, if you play this counting argument and you don't use anything more about the neural network itself, you won't be able to avoid this over parametrization requirement that is still extremely huge compared to what happens in practice. Okay. So this slide is trying to explain the limitation of the proof technique from that original Malak paper. Yeah. Any questions? Any thoughts of how we can improve it? So here's how you can improve it. You can say, so first of all, how did they do pruning here? They just selected one weight, okay? So you have this big sort of diamond structure. You're like, let me find the xi that's closest to the target w. But why not combine them, right? So instead of like just picking one, you can pick the best subset, right? So instead of, still same game, I will like randomly sample xi's, but I won't pick the closest xi, I will pick the subset of xi's that closely approximates my target w. And why can that work? Because here I have a combining layer, all right? Oops. Here I have a combining layer, right? Which means that whatever you choose is going to be added up, all right? So this simple idea gives you an exponential advantage. So combining random weights is exponentially more expressive than picking one weight, all right? So that's the main idea for why this can be better. And this is what leads to, I would argue, an exponential improvement of the over-parameterization requirement. So what we prove in this paper with my students is that essentially any neural network of basically these two dimensions, d by l, can be approximated within epsilon by pruning one that is only a factor of log wider. So the d log blah is the width of the new network. The target network has width d, the random network has width d log blah, all right? And what that blah is basically the only thing that matters, kind of like the error of the approximation here. And this works for whatever random initialization you like. And there's a bunch of extensions that kind of happened after this paper for convolutional neural networks, whatever activations you like, residual skip connections and bias terms or whatever. So this is pretty universal, all right? So again, the statement here is that if you have a target network of this given size, we can approximate it just by pruning, no training involved, okay? And this is existential. It does not tell you how to do it in practice, okay? Any questions? Yes?
What is the runtime complexity of picking the right weights in order to approximate the target network?
For this algorithm, it's it's exponential because it's I guess it depends how you will solve subset sum, right? But it is in the worst case exponential in log 1 over epsilon. So it's polynomial in 1 over epsilon. Yeah. So it's not, I wouldn't use that algorithm, but it's just an algorithm to construct basically it's just for the proof, right? It's not really a usable algorithm. How is that relevant to what we talked before? Okay, so this is my paper, but I didn't just present it because it's my paper. There's kind of like a reason why this will tie back to the whole lottery ticket thing. So this tells us something, right? So this tells us like basically what people were observing for lottery tickets is a limitation of the algorithm. It's not a limitation of pruning at initialization. So here I'm pruning at initialization and I'm telling you something that I hope you think is striking, that like you can literally find, you don't even need to train, right? So you can find lottery tickets that don't need to be trained after. So essentially everything exists. It's not a matter of existence, but it's an algorithmic bottleneck. The reason why IMP fails. So we want to understand if this is kind of like something we can overcome, or is this like an NP hardness type of a wall that we can't overcome? Yes?
In practice, when they use this wide resonance, did they see that they really find the weights of the small network?
No, but it's a different architecture. It's a completely different thing. Yeah. So the match is not one-to-one, it's only a functional match. Yeah. And the proof, like for this subset sum, it's a functional match. Again, it's not a weight-to-weight match. It's a different architecture.
Yeah, but I was just wondering if we should hope to find the exact
Yeah, no. Well, I would argue that that's probably not a good goal. Yeah, just because it will constrain the setting too much. Yeah. Good. Yeah.
So we know that neural networks have other types of symmetries.
Yeah.
For example, like it's scale one layer and then scale the next layer by the inverse. So, and that, all you really care about in a similar spirit, the previous question, is the end-to-end functional.
Correct.
that you're representing. Do you think there's more you can squeeze out of this?
I think so. Yeah, because here the way that we do this is pretty naive in the sense, I mean, it is like, you know, logarithms are like constant, so it's only constant over parametrization, but nevertheless, the way that we do it is very myopic. We just look at the weight, right? Whereas you should be looking at least at the, you know, the linear function of every layer, right? So, but it turns out to be, yeah, it's kind of tricky. Yeah, we weren't able to squeeze more out of that, but that is the right way to do it. Yeah, that's the right way to do it. Yeah. Good. Other questions? All right. So the other thing that's quite interesting is that the signs don't even matter. So you can get the same result with binary networks, all right? If you give me a random binary network, literally random weights, and you just let me, you know, prune stuff, I can still essentially get the same results with a little bit more of an over-parameterization. Again, you know, there's a lot of details to that, but the only thing to understand is that, you know, as long as you have any kind of randomness and you do pruning, you can approximate anything you like on the continuous space of neural networks, of course, within epsilon. So, all right, so how is this relevant to lottery tickets? So this says something about this. So this says that in theory, you can prove that sparse and accurate models exist at initialization. In practice, high accuracy at initialization maybe should be kind of like leading you to high accuracy after initialization. So if I were to take the models from this paper, so they also create some sparse models at initialization, what would happen if I run SGD on them, right? So that's the thing I would like to see. You know, would they, you know, reach state-of-the-art accuracy or no? And what they find is that I'll call them the EP networks, EP is the name of the algorithm, are not fine-tunable at all. That by itself is a striking result that's worth writing a paper on. We still don't understand, like these networks, let's say get you to like 80% accuracy on CIFAR10. If you were to give me like a normally trained network with 80% on CIFAR10 and you were to say run a little bit more of SGD, you would definitely see an improvement. These networks, they don't see any improvement at all. It's as if you're stuck at a weird local minimum. So they're not fine-tunable, right? So again, this seems to be an algorithm that produces a part of the solution, something that has high accuracy at initialization, but it doesn't go any further, okay? Does it make sense? But it does tell you that there are stuff at initialization, okay? So there is definitely some signal, there's some useful information. I would argue that one of the reasons why this algorithm doesn't work well is because if you see it, it kind of like has very aggressive sparsification at every iteration. So they require every layer to have the same sparsity, and they force the sparsity to be that much at every iteration. And although you can get high accuracy at initialization, this doesn't let you fine-tune very well. It's not necessarily true that this is the only reason, but I think this may be one of them. So I want to close this talk by talking about something that is a little bit more than a lottery ticket. We call these things rare gems. And rare gems are going to be accurate networks at initialization that are also lottery tickets, meaning that you can fine-tune them, okay? You can fine-tune it to accuracy that's better than training a random network, all right? So let's see the definition again of lottery tickets. Lottery tickets are sparse networks at initialization, trainable to better accuracy than training a random network. Rare gems are basically lottery tickets that are accurate at initialization as well, so they have an extra requirement, all right? And these are things that our algorithm, J-Miner, finds. And I'll explain to you how the algorithm works. But again, I just want to make sure that the distinction is clear. So the rare gems are lottery tickets. They're special, but they're also special in an extra kind of way. Which way? They're very accurate before you train them, okay? So how do we achieve that? We do some learning before pruning, okay? We do some learning at initialization. I'll try to explain the algorithm. It's pretty simple, and I would argue not very novel. Like ideas like that have appeared in the literature of compressed sensing. But before moving to the algorithm, I just want to take a 3-second pause to make sure that everybody's on the same boat. Any questions? All right, yes.
So about the training, so you said that there is this sparsification when training these. What do you mean? So they don't train it normally? They still like try to prune it every step?
They only prune. So the EP, their Manoogian paper, only prunes. They assign scores to every weight, and the optimization happens on the scores of those weights. And the scores, think of them as survivability scores. So high scores means that those weights will survive the pruning, all right? But the way that they enforce sparsity per layer is a little aggressive. That potentially leads to this kind of deficiency of those networks in regards to fine-tuning. Yeah? Okay. So here's our algorithm. I would argue it's very simple, and I would also argue it's not novel. I'm sure this has been, applied to some other contexts. So you start with W0. This is your initial network, okay? Random initialization, nothing fancy here. And you take a dot product with a rounding function of probability scores P, all right? What is P? So P is going to be between 0 and 1. This is a little bit different than EP. So EP had scores from like minus infinity to infinity, whatever, it doesn't really matter. But you optimize this essentially 0, 1 variable. How does the rounding work? You can choose whatever rounding you like, and we did try a few of them. You can choose randomized rounding. You can choose just this simple rounding where you round everything above half to be equal to 1, okay? This does not create sparse networks, all right? So this creates networks with sparsity roughly 50%. To enforce sparsity, you can do two simple tricks. One is regularization, simplest trick in the book, and the other is iterative freezing. Again, this has been applied before in other contexts, and there's there's nothing too smart going on here. It's just a little bit more, we designed this algorithm a little bit more strategically, let's say. So, again, what's the algorithm? You randomly initialize the weights. You randomly initialize the scores, right? So what are scores? The 0, 1 variables that control whether an edge will be active or not. And you train them using regularization, projected gradient descent, and iterative freezing. If a score becomes too low, that means that you should not be using that mask element. Okay. So this will create what we will call a rare gem, and the rare gem will be fine-tuned with SGD. All right. So you'll just refine the gem with SGD once you find it. Okay. Any questions on the algorithm? Yeah.
So how is it different from the dynamic pruning during training with the magnitude-based pruning?
Sorry, which algorithm?
I think some evidence also proposed to random initialize the weights, and also they proposed to freeze this weight or the mask.
It's the same. Yeah, it's the same thing. But this is on. So this freezing happens on scores, right? So we have like so think of weights, and the weights are frozen, and then think of like a different set of variables on top of the weights, the scores of the weights. And the iterative freezing happens on the scores rather than the weights themselves. Of course, it translates to the freezing of the weights, but yeah. But it's like, again, the algorithm is a combination of other ideas that have appeared in the past. Yeah. But it works, so that's the key. So let me convince you why this works experimentally. So we compare against a bunch of techniques. Of course, IMP is sort of like up here. This is the thing that we would like to see how it performs with warm-up. We are pruning at initialization. We want to make sure that whatever we find is fine-tunable. Remember that Ramanujan EP nets are not fine-tunable. And I also want to make sure that we pass sanity checks. So far, the only algorithm that passes sanity checks is IMP with warm-up, okay? IMP at 0 does not pass sanity checks. And our rare gems are actually passing those sanity checks, okay? So how do we know that? Of course, we can't prove this theoretically, but we run a lot of experiments. So I put all the figures here to convince you that we run stuff. So this thing, my friends, cost around $10,000, okay, on Amazon AWS. Thanks to NSF and all those nice folks that funded us, but nevertheless, it's a lot of money. And this is not even talking about transformers. Right? This is like your friendly resonance and whatnot. Anyways. So let me focus on the data set and model that people seem to obsess about in this literature. So again, this is ResNet 20 plus CFR10. Not that this, whatever I'm going to say now transfers to everything else. I did not cherry pick. In fact, it's one of the worst data sets with regards to performance. But let's just stick to this. ResNet 20 also tends to not be very compressible. That's why you see kind of like the drop in accuracy pretty quickly. So this is again test accuracy up here, and this is sparsity. Let's parse the colors. So the black line here is SGD, just fully dense trained neural network. The yellow one is IMP with warm-up. So we always rewind to like iteration like 3000 or whatever. GM is our algorithm, the magenta is gem miner. And EP is the Ramanujan algorithm that does pruning. And then of course we try to fine tune. And the blue one is smart ratio. This is basically a sanity check where what it does is it says randomly initialize the network, pick sparsity levels carefully, and just train a randomly sampled sparse network. And this blue thing is a hard baseline. Like all the other algorithms that I showed you before, they just don't pass it. IMP with rewinding at 0 doesn't pass that simple sanity check. So if you're above this, that's always a good thing. So you want to be above this blue line. So what we see is that, so the magenta one, so magenta is ours. So the magenta is close to IMP with warm-up. So after we do the fine-tuning, the accuracy of the final network is comparable and sometimes better for high sparsity compared to IMP with warm-up, okay? The pre-fine-tune accuracy, which is what does pre-fine-tune mean? So I find the sparse subnetwork at initialization. I looked at its accuracy without even training, okay? So before even doing any training, you will see that gem miner, or the rare gems, have pretty significant accuracy, like at sparsity 5% or whatever, this is 3 or whatever it is, you have accuracy like around 80%, okay? This is before training the weights. So of course you do learning with pruning, but with a 5% sparse network, you get significant accuracy only by choosing a subnetwork. As you can see, the other thing that's interesting is that IMP and smart ratio, so smart ratio again is like a random network at initialization. How well it will perform? Well, random guessing, right? You don't do anything intelligent. However, I think the interesting bit of information here is that IMP, the claimed lottery tickets, also have random guessing as their performance from the beginning. Okay, so there's nothing, in terms of accuracy, there's nothing exciting that they find. All right. So the EP algorithm also gets good accuracy, but above, not state of the art, but above random guessing. But again, you will see that like the final accuracy is not really much improved for reasons that are still not very clear. But again, the EP nets seem to not be very fine-tunable. Any questions on these two first figures? Okay. So how fast is the algorithm? Oh, sorry, sanity checks first. So we remember those curves that I showed you before? Reshuffling, re-randomizing the weights and all that, or using the 1 over the magnitude as the score. So again, we pass all those tests. So those lines here are kind of like those tests, and this is the performance of the algorithm up here of gem miner. So all those tests that IMP with warm-up passes, we pass as well. And this is the first trainable network at initialization that passes it for those datasets that we tried. Of course, I will keep saying that we partially resolve this problem because we did not run it on every single dataset and every single model. There may be datasets and models where this does not work. I don't know, but at least for the things that people have tried, where it was an open problem for a couple of years, it seems that we do beat all those sanity checks. And in terms of running time, the algorithm is much faster than IMP, so it's around 20 times faster than IMP. So when they run IMP, they use really long training cycles, so around 6,000 pruning epochs. That's a lot of epochs if you're in the business of epochs. So we use 300 epochs, which is comparable to how much fine-tuning we will do after we find the rare gems, all right? So it's a relatively fast algorithm. Probably you can do much faster too, but at least, I would say this is a good improvement for now. We also compare, so remember there were all these other meta approaches where, maybe you can sparsify while you train. So that actually is also a very strong baseline. So this is the dark green or whatever color this is, Renda et al. Algorithm, where they prune while they train. And we find that the performance of our fine-tuned rare gems are comparable to the accuracy that you get from those algorithms. The pruning while training tend to give you better accuracy overall. So we're also competitive with that type of compression. So we have a few minutes and I want to wrap up. I want to tell you a little bit what we covered and tell you a few open problems that I think are interesting. So pruning is used for compression, but what still surprises me is that some kind of learning is actually happening when you choose a sparsification supermask. The amplitudes of the random weights do not really matter. You can prune at initialization even with plus minus 1 random weights. We have theoretical results that tells us that basically whatever failure you see as an algorithmic one and it's not existential, everything exists at initialization. You do not have to worry about it. The way that we overcome the limitations of IMP with warm-up or IMP with rewinding at 0 is by basically finding a very, very accurate subnetwork exactly at initialization, which also tends to be quite fine-tunable. So there's a lot of open questions. I think, in terms of if you're in the business of theory, there's nothing apart from existential results. The algorithm that we have is, I would say it's reasonably fast, but, you still have to deal with a dense model because, you sparsify iteratively. So there's still some work to be done there. And there's something that also kind of bubbled up in discussions with you during the break and during the previous lecture. But we've seen that there are some architectures that are amenable to pruning. So you can take a mobile net, and mobile net is unprunable, all right? But you can take a VGG, and VGG is super prunable, all right? And if you change the structure of the VGG, you change a little bit how the convolutional networks are, or the filters are connected to each other. You can also make it a little bit more amenable with still the same number of parameters, but squeezing out more sparsity. There's also a lot of benefits for considering pruning only, especially in multitask learning settings where you start with a good supermask for a base task, and then you fine-tune the weights for individual tasks. There was a really nice paper by the same authors that the Ramanujan and Wartzman folks from UW that actually did that. It's called Supermasks in Superposition. It's a phenomenal paper as well. I would urge you to take a look. So, any questions? We have 2 more minutes, I think, or something, or is it too fine? 2 more minutes? Okay, yeah. So I have a few more things to say, but this is sort of a recap of the second part. So I just want to see if there's anything that's left hanging.
Super naive, but I'll try anyway. So why L2 regularization instead of L1 to make it even more similar to Prof.
Sorry, can you...
So you mentioned L2 regularization when you train the masks.
Yeah.
I know that you don't call that training, but...
Yes.
Why L2 and not
Yeah.
any other kind of norm?
That's a very good question. So L1 did not... So the reason is that this is what worked. Like, you would expect that L1 would work better, right? Mm-hmm. It did not. Combination, if you did the elastic net, L1 plus L2 works fine. Just L1 does not work. I don't know why. Yeah. But I think, again, this is an algorithm that sort of like resembles, those sort of sparsity-aware compressed sensing type of algorithms. And I'm sure, if you try all of them, something will be better than what we tried here. But yeah, that's a good question. Yeah. Yes?
Regarding the paper that you presented for approximating the smaller network with the larger network and pruning. So if I understood correctly, what's happening is that we have a kind of mini net of that's 2 to approximate the weight each way.
Yeah.
And the approximation lies in what epsilon interval of the weight. But for the final prediction of the network, do you also have a bound, because each of these weights is within epsilon?
Mm-hmm.
Okay, but what about the final?
Correct, yeah. So we have, what happens is you have to combine the individual coordinate-wise approximations to like a bigger one. So the way it goes, like, you start with a single weight, and then you go to a linear function, and then you go to like a full layer, and then with activation. So you have to apply, a bunch of like, triangle inequalities and ellipses type of bounds. But they all kind of like start with the epsilon approximation of the weight, yeah. So this is like a building block, but of course you have to control the epsilon so that like the final epsilon is exactly how much you want it, right? So the actual epsilon that you use, like epsilon over like dimension or something like that, yeah.
And I believe the positive thing is that the epsilon only affects not the depth, but the width.
Correct,
so
yes.
The propagation doesn't.
Yeah, correct, yes. Any other questions? All right, So another thing that I've been looking at, and I think it's very related to that. So again, sparse training is something that's super useful and very interesting, and I would say quite underexplored. There's been some traditional work where you can use like, low rank or sparse type of updates or whatever, but there's some crazy kind of like sparsity aware pruning or training type of algorithms. I don't know if you've seen this. So this is something actually my group is working on. So there's been a paper where they take, pre-trained language models and they have a downstream task and they don't tune the weights, they only tune the batch norm layers. This is sparse training because you only tune a very small subset of parameters. I would argue these are weird parameters because there's only normalization and bias tuning that happens, yet gives you state-of-the-art results for downstream tasks, only training batch norm. The other paper that I also saw, which is I think even more crazy, is you take a pre-trained model, GPT-J or whatever, language again, it has to be a transformer it seems, and you only train the biases of that model, nothing else, right? So the biases typically account for like, 1% or 10%, I guess like less than 10% of the weights, right? Everything else is frozen. You fine-tune biases, state-of-the-art accuracy. Why does that happen? We don't know. But the main point is that there are a ton of different algorithms and heuristics at this point for sparse training. And there's a bunch of different, of course they get similar accuracy, but from the perspective of the system that you run this on, they have different like memory footprint and computational footprint and different parallelization type of properties. And nobody has done a study to see, what's the right way to like sparsely tune a neural network, right? Others are more structured than, let's say, sparse fine-tuning or whatnot, but this is like basically wide open. And it's especially interesting for attention type of architectures. So I think there's a lot of interesting trade-offs, both experimental and theoretical, with regards to like choosing and pruning a good model, because you need high accuracy, you need the model to be easily trainable, and we know that overparameterization helps the trainability, but also burdens any other resource. You want to be fine-tunable and be compact at the same time. And there's a lot of low-hanging fruits, I think, and it's a great area to do research on, and I urge you, if you're not in this general area, to think about it. And if you're wondering what you should work on, this is what it is, transformers. You should work on transformers, okay, yeah. Transformers and attention mechanisms. And I think, it's a really cool time to do research in this whole area, because now, back in the day, like 30 years ago, you could just do like, optimization or like statistics or systems, and you'd be fine. But now there's all these cool problems that lie on the intersection of these different areas. And they require different skills, right? So there's a lot of theory involved in optimization, and there's a lot of systems involved in like architecture and like system design. And you kind of have to know both in terms of like, designing algorithms that are well suited and tailored for like the large scale of problems and systems that we care about. So yeah, I think this is a great place to sort of be in. And on the backdrop is a beautiful Greek island. If you want more information about it, we also act as a tourist guide for Greece. But anyway, thank you so much for attending, and for the invitation. Any questions? Yes?
I think maybe someone already asked this before, but did you compare some other properties of the model that you get, like robustness of the model or something like this? Yeah.
So the one thing I know that people have tried is kind of like fairness metrics, and it seems that there's a lot of discrepancy between loss across subpopulations. So when you do pruning, it seems like the accuracy of particular data points is affected much more than others. There is some work to overcome this and understand this phenomenon a little bit more, but I think this is the most explored kind of like area of like, okay, what happens, to other properties that we care about. And I just want to again emphasize that this is a very valid question, because somehow with this whole model compression literature, we basically project everything that the model does into a single number, its accuracy. But there's so many other things, right? So there's like, there's fairness, there's robustness, there's like, performance on out of distribution samples, there's like, I don't know what, right? And none of that is really, optimized by these algorithms. So I think there is still a lot of work to be done in this space. Cool, yeah.
I have a general question regarding how the process of pruning is done. If I understand correctly, it's an optimization, right?
Right.
And since you don't have access to gradient,
Yep.
how do you drive it?
So you do have access to gradients, right? So once you define trainable, so the trainable parameters now are the 0, 1 variables, right? So why are these trainable? Because you can tune them to be whatever you want. And at the end of the day, you have a nonlinear function of the p variables. Can I train the p variables? Well, there is a little bit of kind of like a trick that you have to play. So let me go back to that sort of figure. There we are. So yeah, so the problem is that you have this rounding function here, right? And this rounding function is not back propagatable. Guess how people replace this? So they replace this with a constant, basically. So you can use something called a straight-through estimator. People typically use this for rounding functions. So on the forward call of the function, you just use the rounding. On the backward call, you replace it with either 1 if the function is active for that given weight, or 0 otherwise, right? So that's basically typically how people do that. Yeah. Yeah. Good. Anything else? Yeah.
So for the gem miner pre-fine-tuning phase,
Yeah.
you're still doing some learning, like you showed us. It's really neat that it works. Did you explore? Do you need to do that pre-fine-tuning training using the entire data set, or what happens if
That's a good question. Yeah.
use a subset?
Yeah, I don't know. In fact, yesterday I saw a paper by Jonathan and collaborators where they used for IMP with warm-up. They said instead of doing it on the full data set, why don't we kind of sub-select a good choice of data to do it? And they find that you can do this, and it works pretty well. So we have not explored that direction at all, but I think it is pretty, of course, meaningful, but also it seems that there is something there. Like people have already seen that this actually does help. Yeah. Yeah. Yes.
Would you have any guideline for somebody wanting to put a large model on the edge, for example?
Yeah.
So it seems to be very specific to the architectural model you're considering.
Yes.
All these methods. So do you see any general guidelines that you could give to somebody willing to reduce the model complexity? Where to start?
Yeah, Google Scholar, I would start there. Yeah, so I know it's an unsatisfactory answer, but the problem is that these things are so dependent on the data set and the setting that, I want to tell you that, yeah, try deep compression. If you don't care about compute, try deep compression, let's say. So in terms of algorithms, I would say, yes, deep compression is a great baseline, right? But maybe you have a particular problem that doesn't work. For example, for attention-based architectures like transformers, unstructured sparse doesn't really work very well. People are able to sparsify, GPTJ or whatever by 40 or 30%, but not down to the level that we're able to sparsify or simplify vision networks. All right. So, if I were to tell you use deep compression, it would work very well for, let's say, ResNets, but you go apply it to, let's say, BERT or GPT something, and it doesn't really work, right? So that's what I mean, that it's very specific to the setting, unfortunately, which is the big one of the biggest issues we have in machine learning. You kind of have to run it for whatever thing that you have and do painful hyperparameter tuning every time. Yeah.
I guess hopefully in a couple of years there will be a framework for that. But
yeah. Well, that's yeah. It's very optimistic, but I don't know. Yeah. I hope there is a framework. Yeah. Let's see. Yeah. Thank you. Yes.
Yeah, maybe I have a related question about the previous Max question. So, what if can we just use the random data as maybe random ticket data did to find your ticket?
Yeah. So which algorithm? The RENDA algorithm? Which algorithm you said?
I think it is in the paper, the random ticket. They argue that only the ratio of the sparsity ratio of the layer matters, and we can also use the random data instead of the real data.
Oh yeah. So we didn't really use random data to find the thing, but I would argue that that's an even easier sanity check to pass, right? So if you pass the sanity check where you re-randomize everything, I would I think probably it should pass it, but this is the problem with experimental. I have to run it. Yeah. So I'll Slack my students and see what they think. Yeah. That's a good question though. Yeah. Great. Well, thank you for a lively set of questions. And yeah, we'll have, I guess, a panel in a little bit to talk more about these things. But yeah, thanks so much.